two simple pendulums of time period 3 seconds and 5 seconds respectively start oscillating simultaneously from their mean position. What is the minimum time elapsed before which they oscillate with the same phase? Okay. So their time periods are given. Well, same phase, that basically means well, yeah, same phase, that means that position and velocity are going to be the same. Well, let's see. No, not necessarily. Actually, wait a second. Yeah, it's not necessary that their position and velocity are going to be same, but yeah, their phase is same. Anyway, let's just do it. So the first one, it has equation x equal to whatever its amplitude is. So say a1 sine of omega 1 t. Cool. And yeah, so we just actually want omega 1 t to be equal to omega 2 t. So omega 1 t is like 2 pi upon capital T. Well, yeah, 2 pi upon omega, that would be t. So yeah, that makes sense. It's just gonna be 2 pi upon 3 seconds into time equal to 2 pi. Wait, but that doesn't make sense. Mean position. Before they oscillate with the same. Okay, so it's gotta be like 2n pi or something like that. So it's gonna be upon 5 seconds plus 2n pi. So their phase is same. That means this must be happening, right? So 2n like t over there. So it's gonna be at time t equals to 0 and oh yeah, this must be the thing. This must be the thing. So just get t into 2 upon 3 minus 2 upon 5 equal to 2n. So t into 5 minus 3 is like 2 upon 15 equal to n. T equals to 15 upon 2n. So first time it happens is when you got 15 by 2 seconds as your t. So 15 by 2 seconds you just get 3 sorry, this should be 5 and then this is just 5 pi, and over here you get 3 and then it's constant 3 pi. So yeah, 5 pi equals to 3 pi plus 2 pi, so 2 pi falls in 2n pi. So I guess 7.5 seconds. Cool. Next question. A uniform cylinder of length L and mass. Was there anything else though? Nah. A uniform cylinder of length capital L and mass m, having cross-sectional area A, is suspended with its vertical length from a fixed point by a massless spring such that half submerged, okay, in a liquid of density D at equilibrium position. Okay, fine. When the cylinder is given a small downward push and release, it starts oscillating vertically with a small amplitude. Okay. If the force constant of the spring is K, the frequency of oscillation of a cylinder is so it's at the equilibrium position. Okay, fine. Let's do this. So it's half submerged, right? Which means that this L by 2, so it's gonna be the force on this is area times the pressure, which is rho water, L by 2 into G. Well, yeah, its mass, well, its mass is, okay, its mass is, wait a second, does that even, there's gotta be something about it. Okay, first of all we need to find the, what happens when it is pulled by X. So that would be rho water Gx times A. Its mass is rho solid, its complete length times, well, what, rho solid times its complete length times area, okay, and the spring, so it's gonna be plus Kx. Does that make sense? So is that going to be its constant? Okay, wait a second. So this is f equals to kx. Fine. Wait, but kx, that's kind of problematic though. Oh, so yeah, maybe we can just find what k is supposed to be. Yeah, that will be doing it. If we can just find what k is, we are done almost. So since at equilibrium position it's half submerged, what we can say is that L by 2 rho water gx, sorry, no, not x, ga, okay, plus the force due to this constant, so k times whatever is the length. Okay, how do we even know what this length is? Can it be compressed? Sure, it can be compressed though. But we don't know what the natural length should be, then how can we even solve this? Oh, so you already have given us the force constant, right? Then why even do all this? So yeah, that looks correct. So that's nice. Okay, so density is d. So it's got kx k plus dga into x upon the mass, which is density, and then all this stuff. Cool. I cannot definitely write the equation though. Yeah. What's the thing that it is half submerged? What does it have to do with? That doesn't make sense. I mean, what was the initial position? Fine. So maybe by half submerged you mean like partially submerged? I don't know. Okay, let's just do this. So it should be this thing upon the density of solid, which I guess we can write in terms of, so it's just m actually. So this is our force, right? Well, yeah. So upon m squared, that would be our acceleration. Wait, no. This was in fact our acceleration. That's why we divided by m. So yeah, that's the acceleration. So this constant is our omega squared. So the frequency, that's going to be square root of all this, which is k plus dga upon m. Yeah. So that's the angular frequency. I guess they want in terms of cycles per second, something like that. Okay, if they want in terms of cycle per second, then it should be this upon 2 pi. Well, yeah, that is correct. So it should just be 1 upon 2 pi square root of k plus ADG. So it should be this thing. Next question. A simple pendulum with length L and mass m of the bob is vibrating with amplitude A. The maximum tension in the spring is simple pendulum. Okay. With amplitude. Well, what amplitude? The angular one or the one with length? Oh, so in the options you only have like A upon L stuff. So it should be the length that we are talking about. Okay. Simple pendulum with length L and mass m is and the maximum tension in the string is, so at the extreme position it has this arc length A. Cool. And this arc length A, well, that is actually sine theta is A. What about cosine theta though? This is so complicated. This arc length is, okay, that's not the best way to be doing it. What can we even do? What's the acceleration of this? Well, that would be the torque. So, okay. So the torque, no, actually not even torque, the angular acceleration, that is g by L theta, I believe. Minus g by L theta. Yes, it's like that. Okay, cool. So now we just want to convert it into the actual acceleration, which is like just multiplies by L. So that just gives acceleration, right? The tangential acceleration equals to minus g by L into tangential velocity. Oh, well, sorry, no, not the tangential velocity. Theta L would be the displacement. Cool. Then the maximum tension in the spring is what? Okay, maximum tension. Well, yeah, so maximum tension will be at the lowermost point. So we just need to find what will be the velocity. Velocity will be like, so just got half kx squared, well, kx squared, k times amplitude squared. Have we been given the amplitude? Yes. So amplitude squared into angular frequency squared, kx squared, right? So yeah, this thing also squared equals to v squared. So it's the v at that thing. Okay, divide this by L, so v squared by r, that would be the acceleration need. So it should be cubed over there. Looks correct. Yes. That's nice. So now what? Now this thing, well, okay, so that should be the acceleration. So it's more like the tension upon the mass. So our tension is just ma squared g squared upon L cube. Something doesn't feel correct though. Okay, that's the tension because of plus mg. Yeah, plus mg because it also has to account for the gravity. So this will be mg into 1 plus squared by L cubed. Something is not right. A squared g squared by L. What's going wrong? It should be the frequency squared times x squared is like the amplitude. The amplitude is, right, that looks correct. Then v squared by r is the acceleration for sure. So this should be correct, right? But it's not. Just not. Why? mg into 1 plus a squared by r, L cubed into g. Well, that's not quite what I wanted. Where am I going wrong? Why is this g over there? It should be like square root and stuff. Sorry. So it should just be k over. Why am I making so many mistakes? So this is supposed to be g upon L, but then that L gives it g upon L squared. So just put g upon L squared over there. Sorry. Yeah, silly mistake. That g is gone, so just like that. Oh, it's a squared over there, so that as well. Nice. So this should be this one. Next question. A block of mass m attached to a fixed position O on a smooth inclined wedge of mass capital M oscillates with angular frequency, if an amplitude A and linear frequency f. Okay, the wedge is located on a rough horizontal surface. Oh, so when it is attached to a smooth inclined plane, it oscillates with angular frequency. It oscillates with amplitude A and linear frequency f. Cool. So now the wedge is located on a. Oh, so this wedge is smooth, but it's located on a rough surface. If the angle of wedge is 60 degrees, then the force of friction acting on the wedge is given by. Okay, so we having given the coefficient static friction. Yeah, angle of wedge is 60 degrees. Okay. the force on the friction. That's not good. What even is it supposed to be? Well, it's just going up, right? There's definitely that force acting. Okay, there's mg acting on this guy. It has to provide normal force to not let that go down. There's this force on this wedge as well. Since its static friction is given, that means that it must not be moving. Yeah, it remains stationary. Cool. So let's just do this. The force of friction acting on the wedge is given by, well, let's try to do it. Okay, so everywhere you see mu, but why? Question static. It's more like the maximum force that can be acting. Okay, well, let's just try to do it and see what we get. So you got this guy, and there's this thing. You're applying some normal force on this guy to keep it from falling. The acceleration in this direction is mg cosine theta. So your normal force must be such that it balances it. So this must also be mg cosine theta. That's normal force that this guy receives. So I'm just gonna draw it like this. Okay, then there's this force pulling it like that. So you just got kx in this direction, so you also got kx in this direction. There's this mg cosine theta. What's theta, by the way? It's 60 degrees, so it's just going to be mg by 2 in this direction. And there's this kx thing in this direction as well, right? We have been given the angular frequency and everything. Okay, cool. So x varies as a function, right? So we got kx, it's making 60 degree. This angle is 60 degrees. Nice. This angle is 60 degree as well. So this horizontal direction is gonna be kx upon 2, and in this direction, what's the force? Well, it will be because of this thing. So it's 30 degree, right? So cosine 30 degrees, that's gonna be square root 3 by 2. So it's gonna be square root 3 mg upon 4 in this direction. So the net thing is just square root 3 of mg upon 4 minus kx by 2. Okay, what do we know? We know like kx minus mg sine. Yeah, it's complicated. Well, at the equilibrium it would be like this. Okay, fine. So it's just gonna be kx in that case. Sure. So yeah, well, for the equilibrium position, okay, so this does change as a function of omega, but we'll just see what we get. Well, at the equilibrium position, what's the force that it should be giving? Kx at equilibrium, this should be mg sine theta. Cool. So that's the force. So this is F at equilibrium. The F dash force at any position, that would be kx naught plus k delta x, which is mg sine theta plus k delta x. And this is the actual net thing. This will be the net force in this direction on this block. So that means k delta x upon m. This is our acceleration. So our acceleration is like, actually it's minus of that. So k upon m, well, yeah, k upon m, that, in fact we just want to eliminate k, right? Okay, so k upon m, this is the angular frequency squared. So just get k equals to m omega squared. And this delta x thing is like very small compared to x naught. So we can just say like f dash is approximately f. Cool. So this is just gonna be k. Well, in fact, we already know what this thing is, right? We know what this is. K is mg sine theta. At the equilibrium position, it's gonna be mg sine theta. Right. Well, we also know it's gonna be m omega squared. So we can find what x naught is. Yeah, but that's not what we want. Should we just like put this force over there? Well, yeah, we should. Maybe sine theta. Well, it's gonna be square root of 3 by 2, I guess. Oh, sorry. What was there? Once again, upon 2. So, oh, so this would be a negligible quantity in that case. So we do need this extra force. Yeah, we need this extra bit. It's gonna be minus this guy, which is square root 3 by 4 mg minus k delta x upon 2. So minus plus whatever. In the end, it just cancels. Now we know what k is. Well, do we know what? Yeah, in fact, we know what delta x is as a function of t. Nice. This cancels, and that's what we are left with. We just need to calculate what this thing is. We know what k is. It's just m omega squared. Yep. M omega squared delta x. Delta x is just the amplitude. Have we been given amplitude? Yeah. Times sine of. So they gave f, but they are using omega. Well, whatever. So sine of omega t. Nice. That should be the thing. So it's just m omega squared. Wait, half of that, right? Well, yeah. So 1 by 2. Half m omega squared a sine omega t. Well, that's in this direction. So yes, that's the thing. Next question. A mass m is suspended from a spring of force constant k and just touches another identical spring fixed to the floor as shown in the figure. Oh, it just touches, right? The time period of the small oscillation is okay. Right. Wait a second, but that doesn't. So it's not attached to the spring. It's not attached to this spring. Well, that's problematic. So when it goes up, okay, it just think. Well, there's gonna be this force and that force at the same time because they're in parallel. So for one half, it experiences more force than the other half. That is bad. That's really bad. But we know that this, yeah, I mean, like, it still does act somewhat like a linear thing, but the line is different. Small oscillation. So we need to find this for this thing and then that thing and then add those two. Oh, it's gonna be complicated. Well, anyway, let's just do it. So for the lower part, we will have to consider it as attached like this. So shifting it by a little bit x, that will result in kx plus kx as the net force on it. So it's gonna be 2kx, more like 2k upon mx. That's the acceleration, right? Negative and stuff, but you get it. So this is our omega squared. So omega would just be square root of 2k upon m. So just get 2 pi upon square root of 2k upon m. But in fact, it's gonna be pi upon square root of, because it's gonna be half the time only. So it goes and returns, that's t by 2. Now it does the same for that as well. So it's gonna be pi upon square root of k by m. That's kind of weird. So this should be pi square root of m upon 2k plus pi square root of m upon k. Nice. Which is, well, this would be 2m upon, no, that's not going on. This guy. Nice. So yeah, that was it. Okay, I will see you in the next video. Bye.